All right, it's 1:20. So let's see, we have 35 of you, which is not bad. As we talked about before, this being World Mental Health Weekend, the university's given everyone the day off, sort of. You still have to watch the lecture at some point, and I still have to record it at some point, so it doesn't really feel like a day off to me. But I appreciate some of you showing up, so I'm just not talking to an empty screen. I do a lot of that for the lab videos, and it's not as much fun. So good. 37 of us now. Okay. Let's see. Announcements, nothing major. Just the homework is due on Wednesday. And I'm moving my office hours next week, as I talked about last time, from Thursday to Tuesday. So you can have an office hours before the homework is due, because this is a trickier homework, as we talked about, very mathematical, certainly not something you want to put off to the last minute. And it's about, if we discover a new world out there in the solar system, which we do all the time, what are the basic observables, the simplest things to observe, and what can we figure out from those basic observables? What are the bulk properties, the bulk characteristics of that new world? Whether it's a planet or a dwarf planet or an asteroid or a Kuiper Belt object or a comet or whatever it happens to be. And so this homework, you're walking through those steps, and that's where we left off in class last time. I gave you enough math to do the first 6 questions of the 10-question homework, and hopefully you at least started or took a look. Some people showed up for office hours yesterday, so they were working on it. That's good. Let's do a warm-up question, and I'll have another one or two on Monday, all connected to this. So last time we got up to the point of measuring diameters of worlds, physical diameters. The angular diameter is easy. You take a picture, how big is it in the picture? It's an angle. But how big is it physically? Depends on the distance. So here's a warm-up question. Jupiter is 5.2 AU from the sun, not from us, from the sun. Its angular diameter at closest approach to Earth is 50 arc seconds. If we were to look at it from the sun, it would be a little bit smaller, but we are closer to it than the sun, and we measure 50 arc seconds. Use this information to calculate Jupiter's diameter in Earth diameters. And you'll use the equation that we ended with last time. So I'll give you about a minute or so to work through this. A couple steps, a little bit tricky.
Dr. Reinhardt?
Yeah.
I was wondering, so does the equation that you gave us last time for diameter calculate it into Earth diameters, or is it into kilometers?
It will be in whatever units you use for the distance. And so here we've given the distance in AU. Again, that's the distance from the sun, not the distance from Earth at closest approach. You'll want to figure that out. But you put that distance in astronomical units, and the size of the world will come out in astronomical units. So you can either convert to Earth diameters before or after. In my answer sheet here, I did it before. I took the distance from Earth and calculated and converted that to Earth diameters and then plugged it in. Give you another 20 seconds or so. Okay, you can keep working on it. I'm just going to take a look and see what we have so far. Let's see, we got some really big numbers. This is what, 40,000, and this is 200 million. I'll cut it off maybe around 1,000. Okay, maybe add some bins. But yeah, most of you got it, 12. So let's work through the math for that. Do the slow reveal here. Okay, so there's our basic, one second. Our basic equation. Angular diameter divided by 360 degrees is the physical diameter divided by 2 pi times the distance from us. So solving for diameter yields this. Okay. At closest approach to Earth, Jupiter is 4.2 AU away, and it seems most of you got that. I'm willing to bet, let's see, if you forgot to subtract that off, your distance was a little bit too high, so your diameter is a little bit too high. So I'm willing to bet those of you here under the 15 probably forgot to subtract off the 1 AU. That's the, 5.2 is the distance of Jupiter from the sun, but we're taking the picture from Earth. And since we're at closest approach to Jupiter and Earth's 1 AU from the sun, that's a 1 AU difference. And you'll need to remember to do that in the homework as well. The one in the homework, it doesn't matter as much because the object's much farther away. So 1 AU is a smaller fraction of the whole, but still, it's worth a point to remember that. Okay, so 4.2 AU away. And I decided to convert that to Earth diameters at the beginning. I could have kept it in AU and I would have gotten the diameter of Jupiter in AU and then convert after the fact. And that's what we do in the homework. But here I did it to the distance of 4.2 AU. And I gave you in the problem 1 AU is 12,000 Earth diameters. So that means the distance between us and Jupiter is 50,000 Earths. You can put 50,000 Earths in a line and fill the space between us. And also, we got to get the arc seconds, the angle from arc seconds into degrees. And I said it's 50 arc seconds. We've got 60 arc seconds in an arc minute, 60 arc minutes in a degree, so 0.014 degrees. If you didn't do that, you're probably high by a factor of 100-ish. And so that would be, there may have been a little group above 1,000. Let's see. Yeah, I don't know if I can back out, but anyway, so 0.014 degrees. Then you plug it all in. 2 pi times 50,000 Earth diameters times 0.014 divided by 360, and you come up with 12. So good, most of you got that. Any questions about that? Or about anything else so far?
Work up there for like 10 more seconds. I was just copying on the last part of it.
Absolutely. And I'll, of course, post these shortly before the exam, but it's nice to have now as you're working on the homework.
When is the exam?
It's in the syllabus. Let me take a look. Now it's on my calendar too. That should be easy to find. On the 30th, it's distributed on the 30th and due on the 31st.
Thank you.
Which is getting pretty close to the end of the semester. The last 3 lessons are really short, so.
Oh, and where did we get the 50 arc seconds again from? I think I missed that part.
Oh, that was given.
Oh, okay.
Yep.
So this is the French. Okay.
Okay, cool. And also you can always print screen, right? Screen capture and grab that real quick. Okay, so let's keep going on this table here. Well, actually, I think I have a few more slides having to do with the diameter. But again, what we're doing is we're going through this table and figuring out where all these numbers come from. We just did the diameters and we talked about the sizes. There's Jupiter, it's actually 11.2, so we must have rounded a few things off. But Jupiter and Saturn are about 10 times the size of the Earth, Uranus and Neptune about 4 times. Here's a comparison, Jupiter, Saturn, Uranus, Neptune. Here's the Earth and Venus, just a little bit smaller. Mars, Mercury, and they put Pluto here. Back when it was a planet, I guess. They included it in the family photo here. And this just puts it in perspective. Again, the sun is 100 times the size of the Earth. So it's about 10 times the size of Jupiter, roughly. And so just, we're pretty small. And, you know, stars can get a lot bigger than this as well. A lot smaller too, but a lot bigger as well, like 1,000 times bigger. Okay, next let's go back and get the mass. And this is question 7 in the homework. And it's perhaps the trickiest one. So it's worth spending a little bit of time to make sure we understand it. Maybe I'll go to full screen here. Okay. So how to figure out the mass of a world? What equation would we use for that? Does anyone recall? Well, if you're in the lab course, you used in lab 3. See, when fewer people show up, then my odds of getting an answer go down. But
Dr. Eckert, I have an equation for mass.
Yeah.
Is it isn't it a cubed over, was it p squared?
Yep, that's it. So very good. And that's if it's in the proper units. So I'll back out a little bit and get to that point, but great. And what that is Kepler's third law, but Newton's form of it. And remember, Kepler said p squared is proportional to a cubed, but I don't know what the constant proportionality is. It's different for different central bodies. Newton figured out that it depends on the mass. And he came up with, so this is Newton's form of Kepler's third law. P squared is 4 pi squared over g times the sum of the two masses times a cubed, where big M is the central body. In this case, we're talking about the planet. So, you know, in the homework, the fictitious world I've given you has a moon. And for most of the planets, this is the easiest way to measure the mass. If there's a moon going around it, you can say how massive must it be for it to orbit that way. Some planets don't have a moon, and so we have to try some other tricks. We'll get back to that. But assume that the world has a moon and we can use it. This is the mass of the orbiting body. So in this case, the moon. But we can apply this for planets going around stars, etc. Now, we're going to make a simplification here. We're going to forget about the mass of the orbiting body. We're going to assume it's really small compared to the central mass. So it's just a very small source of error. We can drop it, neglect it. So in this case, we have p squared is approximately equal to 4 pi squared over gm a cubed. Or we could just write p squared, p squared is proportional to a cubed over m, because 4 pi squared over g, they're all constants. Or we can solve for m, we get m is proportional to a cubed over p squared, which is the equation you just gave me. But actually, I think what you gave me was m equals a cubed over p squared. And that's fine as long as you use consistent units. Again, this whole thing with ratio problems, you can simplify them if you use the units of a comparison body. And the units that we're going to be using in the homework are, put the semi-major axis in AU, the orbital period in years, and the mass in this case comes out in solar masses. That's the symbol for sun, so solar masses. And I'll prove to you in just a second that this is fair. When you were doing Kepler's third just by itself, like planets going around the sun, you just use p squared equals a cubed and use the units of years and AUs. But here we do this and we get the mass and central masses. So let me
Professor Record,
yeah.
What does G represent?
G is the Newton's gravitational constant.
Okay, thank you.
Strength of the gravitational force. It's a constant, a fundamental concept of nature. Okay, so why do these units work? You've seen all this kind of stuff before. This is the long way of doing it, but I'll just do it one more time, can't hurt. M proportional to this stuff means M is equal to some constant times A cubed over P squared. And this is the general case. True for anything going around anything, moons around planets, planets around stars. And then our comparison case will be Earth going around the sun. So that's one solar mass equals this constant. The constant is just, the G and the 4 pi squared times 1 AU cubed over 1 year squared. That's the case for Earth going around the sun. That's the orbital period, semi-major axis, and mass of the central body. So we just divide those equations and the constants cancel out. And we get, move it over here, mass measured in solar masses is equal to the semi-major axis measured in AU, quantity cubed, divided by the orbital period measured in years, quantity squared, or again, just M equals A cubed over P squared, as long as you remember to use the correct units.
Sorry, what is M measured in?
M in solar masses. So this M with the little circle and a dot, that's the unit actually. That means mass of the sun. This, for example, would be mass of Earth. That's the symbol for Earth. Just giving you a second to get all that down. Okay, so let's think of it in context of the homework question. Okay, gonna move this now. So in the homework question, well, even before the homework question, let's just continue our list of observables here. And we started with the orbital period of planet X and the angular size of planet X. We've used those already. And so now we're adding 2 more observables. That is the orbital period of the moon going around planet X and the semi-major axis. It's the angular, so it's the, I'll just write out angular distance of the moon from planet X. So let's draw it out. We have planet X here, and we have some moon that we image around it. And we watch the moon, and in the question in the homework, the problem in the homework, it has an orbital period of 1 month. We watch it, and it's going around once every month, like our moon does. And the other thing that we can get, just from the image, suppose you take a picture, and we know the angular size, that planet X has a particular angular size. And just looking at the picture, we can say, okay, this moon is 1, 2, 3, 4, 5, 6, 13, 14, 15. 15 times the planet X diameter. That's the semi-major axis, for a circular orbit anyway. So we have the orbital period in months and the semi-major axis as a multiple of the size of the planet. It's just something you can read off the image. How big's the planet? How far is the moon? What's that ratio? In the problem I'm giving you in the homework, it's 15 times farther away than the size of the planet. Now, this is all problem number 7. In problem 6, you calculated the size of the planet in astronomical units. So you can then take that size in astronomical units certain number of AU. It's going to be a very small number. Multiply it by 15, and you have the semi-major axis as some number of astronomical units. And the orbital period is 1 month. That's easy enough to convert to years, 12 months in a year. So you can use the equation that we had on the other page. Mass is A cubed over P squared. Or again, the A is in semi-major axis. A is in astronomical units. So you take this number, plug it in here, orbital period in years, plug it in here, and what comes out is the mass of the central body, the mass of planet X in solar masses. Follow the steps? Okay. Now, that's number 7. Number 8. Go ahead.
Sorry, can I just ask a quick question to clarify? So the mass in solar masses will come out as a proportion of it compared to the sun?
That's right. It'll
Okay.
be the mass of that central body, in this case, a planet, and it'll be in solar masses just because those are the consistent units of our comparison. And so it should be a tiny number of solar masses. And then in question 8, you're going to convert that to Earth masses and kilograms. Earth masses, just to put it into context, if this is a planet, it should be a tiny number of solar masses. It's hard to get a feel for what that is. But if it's like 4 Earth masses or 20 Earth masses, that gives you an idea for the mass of the planet, or 1/10 of an Earth mass, that kind of thing. So we'll convert it to Earth masses, and at the same time, we'll convert it to kilograms because you'll need that in the next question.
I have another quick question.
Yeah.
Since it says the orbital period is 30 days, do we just assume that's a month, or would we just do 30 over 365? Does
You
it
could
matter?
you could do either. I forget what I wrote in the homework question, whether I said 30 days or 1 month, but
I think it was 30 days.
okay, then divide by 365 and it'll be about the same.
Okay, thank you.
Okay,
I have a
good.
quick question.
Yeah.
For that semi-major axis, 15 times the planet, is that times the diameter, or is that in
It's times the diameter. Yep.
okay. All right. Thank you.
And you have the diameter in AU from the previous question. They all kind of build off each other. Okay. So before we do other parts of the table, let me see, shrink this a little bit. Yeah, so that's the diagram I just drew. Before we do other parts of the table, let's talk about what happens if you don't have a moon. Like here, Mercury and Venus, they don't have moons. And so, but we know the mass of these worlds here. And well, let's look at the masses here, and then we'll talk about how we know the mass of Mercury and Venus. The Mercury is only 5% the mass of Earth. Venus is 80%, 82%, so it's similar to the Earth. The moon is minuscule, 1% the mass. Mars is only 11%, so it's a very low mass body. Asteroids are nothing, comets are nothing. But out here, Jupiter's about 300 times, and Saturn's about 100 times, and Uranus and Neptune are about 15 times. And of course, the sun is huge. But yeah, back to the question of how do we know the mass for Mercury and Venus if there are no moons to use? Just looking at it, we can't figure out its mass just by looking at it. We got to see its gravitational effect. So what could we do? If we don't have a moon, what could we do? Anyone want to speculate? Don't have to speculate.
This
Well,
might
let's-
not have been a
Go ahead.
viable thing until recently, but we could send like satellites or other spacecraft in orbit and then see the planet's effect on that.
Yep, that's what I was looking for next. So if you want to get the mass, ideally you have a moon and you can just watch it and then you're good. And by that, I mean a natural moon. But if there's no natural moon, you can give it an artificial one. We can send a spacecraft and put it in orbit and then do the same calculation. Though in reality, you kind of want to know the mass before you try to put it in orbit, because if you put it in orbit with too much velocity, you'll just keep going, or too little, it will crash into the planet. I guess you could take a buckshot approach, just build like 1,000 little satellites and send them out there with different assumptions about the mass and see which ones land into orbit, but that's very costly. Well, fortunately, we don't have to do that. We don't actually even need to go into orbit. If we just flew by it and watch how much we're deflected, you can calculate the mass. A low mass body won't deflect you much. A high mass body will deflect you a lot. But still, before we send a spacecraft out there in space, we like to know exactly where it's going. But there are other things that fly by planets. Sometimes an asteroid gets close, or a comet, or the planets just pass by each other. So they're natural gravitational interactions. Remember Neptune, it was discovered because we saw something tugging on Uranus and could figure out how massive that thing was. We can look at our own orbit. Something's tugging on us. And every time Venus goes by, there's a distortion. And we can figure out the mass of Venus, even though it has no moons, just from how it's disturbing our orbit. And then we look at Venus's orbit and it's being disturbed. And so we can, by Mercury, every time Mercury goes by, and we can figure out the mass of Mercury. Of course, there are other things disturbing our orbit. Jupiter's disturbing everybody's orbit. And so there are all sorts of these little interactions, but we can figure them all out and figure out the masses of Mercury and Venus, even though there are no moons, without having to send armadas of spacecraft to maybe go into orbit. Okay, that's how we did that. Let's see what's next in the table here. Number of known satellites. This figure is from 2008, so it's pretty outdated, but I think I gave you a list of moon numbers last time, and if not, I have a list in front of me. I'm not sure how old that is either, but nothing's changed until you get out to the gas giants, and the numbers I have in front of me, which are probably 1 or 2 years old instead of 12 years old, 79, 82, 27, same for Uranus, 14 for Neptune, 5 for Pluto. So the numbers keep increasing as our technology gets better. We pick off smaller and smaller ones. And particularly as we go and visit these worlds, we tend to find more of them. Okay, next column is rotation period. And if you want to figure out how long it takes a body to go around, what do? What's one thing you can do? Take Mars. That's a simple case. We know Mars orbits about once every day. We can see that here. Yep, Mars's rotation is about the same as our own, which is good if we do want to colonize it. We don't have to change our sleep schedule too much. But how do we know it's once a day?
Do you take multiple observations and compare the faces that you see?
Yeah, that's right. Different sides of Mars have different surface features. So we can make use of, let me write some of these things down. We can make use, so this is under rotation. We can make use of surface features. And that's great if you have surface features to look at, but sometimes you don't have any surface features because it could be covered in clouds, like Venus, for example. Yeah. Well, in that case, we still have a couple options. We can use radar. We can send a spacecraft there with radar capabilities that penetrate through the clouds and map the surface and see the surface features underneath. So we can use radar to, again, get surface features. Or we can just do a Doppler measurement. Even before we could send a spacecraft to Venus to orbit and make a nice map through the clouds, we could just send a bunch of radio waves, bounce them off Venus, they come back. One side's moving towards us, one side's moving away. So the side moving towards us, it comes back blue shifted. The side that's moving away comes back red shifted. So we send out one wavelength and we get a range of wavelengths back, and we can use that to measure the rotation. And then you have worlds like the gas giants that don't have surfaces. It's clouds all the way down, gas all the way down. There may be something down at the core, but we'll never get to it. For those, we use the magnetic field. The magnetic field of the world, as we'll learn, is tied to the core. And so we can observe Usually in radio wavelengths, we can see magnetic fields, or electrons spiraling through magnetic fields make radio waves. So we can watch the magnetic field go around, and that tells us the rotation rate of the core. The clouds may be moving at whatever speed, but the core, we get that from the field. So knowing that, we can look at the table here, and you see Mercury and Venus are really slow rotators. And there are reasons for that we'll get to. And Venus has a negative sign. It's going backwards. Everything in the solar system, for the most part, is going counterclockwise as you from the top down. The orbits, rotations, orbits of moons, rotations of moons. But you do have a few exceptions. Venus is very slowly rotating clockwise, backwards. We'll have to explain that. The moon, as we talked about, its rotation is tidally locked to us, so its rotation rate's the same as its orbital period. Mars is about a day, and then you get out here among the gas giants, and they go around in about half a day or so. Even though they're huge, they're spinning faster, so it's pretty rapid motion around the equator. And Uranus, you can see, is negative as well. It's tipped over. It's just slightly, it's actually on its side. And we'll see that a lot of these can be due to collisions, planet-to-planet collisions in the formation of the solar system. The sun goes around about once a month. We track sunspots for that. Okay, the last column here is the average density. And so let's go back to the dot cam. I'll get a fresh sheet for that. Okay, average density. And this is useful because it tells us a lot about the likely composition of what the world's made of. So does anyone remember density is what divided by what?
Mass over volume.
Yep, mass over volume. And the volume of a sphere is, you may or may not remember, I'll just tell you, 4 pi over 3 times the radius cubed. So we can plug that in and you end up with 3m over 4 pi r cubed. So average density is given by this. And the radius of the body, we've already calculated the diameter back in question 5. So you take that diameter, cut it in half. So from number 5, you have the diameter, it goes here. And let's see, we want the diameter in kilometers. Yeah, in number 5, we have the diameter in kilometers, that's right. And you get the radius, and then that can go in here. And the mass, you want that in kilograms. You can see the units here, kilograms per meter cubed. And in question 8, we had the mass in kilograms. Meters and kilograms. So you plug that stuff in and you get the density. And let's look at some of the densities that we have here. It's listed in kilograms per cubic meter, that's the MKS system, but also grams per cubic centimeter. Some astronomers still use this kind of older convention, but we'll stick with kilograms per cubic meter. And we see in the inner solar system, it's higher, 5,000s. And then you get out to the moon and Mars, get into the 3,000s, and the asteroid belt 2,000s, and then gas giants 1,000 to 2,000. And so let me give you some comparisons to put that in context. Now, I'm not saying, I mean, some of these are not what the world's made of, but just to give you some feel for what these numbers are. Like take water, just water in your glass, in the ocean, in the bathtub. In ice, its density is pretty similar. Water or ice, that's 1,000 kilograms per cubic meter. Now, we saw with the gas giants, they're all around 1,000. That doesn't mean that they're made of water. Compressed gas. We know gas is normally less dense than water, like the air about me here is less dense than water. But if you compress it under gravity, like take all the mass of Jupiter, squeezing that together, you get densities also of about 1,000 kilograms per cubic meter. The average density of the sun is about 1,000. So on average, the sun, the gas in the sun, the gas in the gas giants are as dense as water. In fact, if we look at Saturn, it's a little bit below 1,000. which means if you had a giant bathtub in some gravitational direction, Saturn would float in the bathtub. It's less dense than water. But they're made of, go ahead.
Sorry. Why does the gas stay as a gas? Why doesn't it like condense into like a liquid or something else?
It's all about temperature, pressure, and the type of gas. If you take water vapor and make it, in the air, make it cold enough it liquefies, make it cold enough it solidifies. But that's difference in temperature, but also difference in pressure can change it as well. The behavior of the gas in the gas giants is very much like a liquid because it's compressed so close together that it behaves like a liquid, though it's still technically a gas until you get to the very center.
Thank you.
We'll see some of the strange stuff with that here on Earth as well. We get down in the core, we have liquid iron, but we also have, due to pressure, in the outer core, it's liquid iron. You go deeper in where it's hotter, you'd think it would be even more like a liquid because it's hotter, but it's actually solid because pressure changes it. Okay, water, compressed gas, rock. Rock is typically about 2,000 to 3,000 kilograms per cubic meter. And then you have metals. The most common type of metal in these worlds is iron, and iron is about 8,000. These are all kilograms per cubic meter. So again, if we go back to these numbers here, looking at Mercury, Venus, Earth in the 5,000s, that's kind of between the rock and metal range. And lo and behold, we're a mixture of rock and metal. So the density can tell you something. The moon, 3,300, it's just a little bit above the rock range, which means it's primarily rock with a little bit of metal, and same with Mars. But then we get the asteroid belt, that's definitely in the rock range. There's some metal there too, but more rocky. Then out here, these are compressed gases and ices, something like Pluto that is a solid. It's basically a big snowball, essentially. And same with comets, though their density is a lot lower. It's like a very loosely packed snowball. Okay. So that should be everything you need to do the homework. Density is question 9. And then the final question, question 10 is, okay, given the mass of this world, given the size of this world, given the density of this world, what's it like? And you can use this table, or I think I have this or a similar table in the homework for comparison. And you can tell me what kind of world we're talking about.
Can you go back to the dot cam with the density?
Yes. Okay, so I have about 10 minutes, 12 minutes left, and I'm going to get us into the last part of lesson 5. You don't need it for the homework, but lesson 5 is an introduction to the rest. And so we talked about discovering new worlds. And so now let's talk a little bit about their exploration and the spacecraft that we've sent out to them. So I can reference back. When we get into planet by planet, I'll talk less about which spacecraft, and I can just refer to them. Well, Cassini did this and Juno did that. And so let's just kind of summarize the exploration of the solar system. Oh, a couple slides before that. First, just to wrap up from this table, you probably noticed there are 2 major classes. The worlds that are close to the sun, the terrestrial worlds going out to Mars, and then the gas giants. They both have different properties from each other, but similar properties to themselves. And this is just kind of a summary of that. And these are things that we'll need to explain over the rest of the course. We have the terrestrial planets here, the Jovian planets here. Terrestrial planets are close to the sun, Jovian planets are far from the sun. And that actually determines a lot of the following properties, as we'll find out. Closely spaced orbits versus widely spaced orbits, small masses and sizes versus large masses and sizes, predominantly rocky, predominantly gaseous. The terrestrial worlds have solid surfaces, the Jovian planets don't. As we just saw, they have higher densities, Jovian ones lower densities. We rotate slower, they rotate faster. wasn't in the table, but we tend to have weaker magnetic fields. Earth is an exception, and they tend to have stronger magnetic fields, especially Jupiter. And we have few, if any, rings or moons and no rings, and they have many moons and many rings. So we already see there are two broad categories just from the bulk observables, and we'll need to explain that. Okay, but now into exploration of the solar system. This is just a figure from the textbook. It's out of date. The textbook probably has a new one, and you don't need to know all this information. But I just put it up here. These are the missions to the inner solar system planets, Mercury, Venus, and Mars. And we see a variety of different types of missions going all the way back to the 60s. That's kind of when we started, the mid and late 60s. We have some that just flew by. That's the easiest thing you can do. You can also go into orbit. So we have orbiting missions. We have ones that do atmospheric studies where they'll fly through the atmosphere or drop a probe through the atmosphere. Here's one atmospheric probe going into Venus. We have ones that land on the surface. And some we've crash landed, but some designed to land. And some of those are stationary, but some of the more advanced ones have little rovers. They either are rovers or they carry rovers that can then venture out. So there are all sorts of different levels of exploration. So I'm going to go through first the inner solar system, just show you a few slides for each one, just to kind of introduce the topic, wet the whistle, and we'll hit each of these in greater detail. So this is Mercury. This is probably the best picture of Mercury that you can do from the ground. Again, it's really hard to observe because it's so close to the sun. You can't get much detail. There may be hints of craters on the terminator there. And we didn't know what it looked like for the longest time until we sent out the MESSENGER probe this kind of past decade. And this mission's over now, but it was a pretty recent mission, ending just a couple years ago. And it flew by Mercury 3 times and then went into orbit. There was another one that we had a flyby earlier as well that we'll talk about. But just in the past decade, we've acquired detailed images of Mercury. It looks a lot like our moon, but there are some differences as well that we'll talk about. But pictures like this amaze me, that we can get this close to Mercury and see what the surface is like. That's new. Then there's Venus, and this is what it looks like to us. It's just covered in clouds. For a long time, it was a mystery what was underneath those clouds. And, we sent missions back in the 70s as well, but the most recent big mission was Magellan. You can see it being launched from the space shuttle here. And it went in orbit and had radar technology so it could penetrate those clouds. It has total cloud cover, so we never saw the surface. And so this is computer generated from that radar data. They send radio waves down through the clouds. It bounces off and comes back. It bounced off a mountain. It comes back a little bit faster than if it traveled down through a valley and back up. And so there's timing difference and also reflectivity. Some regions reflect more, some reflect less. And they covered most of the planets. Look, they didn't quite get the polar region down here, but you see what looks like and is lava flows on tremendous scales. This place is covered in volcanoes. And the nice thing is, since it's just data, we can plot it any way we want. No one ever stood at this position and looked in this direction, but we can take that elevation data and just print it up in perspective. And this is what it would be like to be like flying over Venus at low elevation. You just see volcanoes and lava flows everywhere. We have landed on Venus. Mostly the Soviets did. Americans did as well. But the Americans said, we're going after Mars, and the Soviets said they're going after Venus. In fact, even like 2 weeks ago, the Russians said Venus is ours, and then they're refocusing their efforts on Venus. There's some interesting news about organic compounds in the atmosphere of Venus that may be due to some microbe in the atmosphere, or it may have a non-biological origin. Anyway, Venus is interesting. But this is a picture. This is taken by the Soviets, one of their landers on the surface. And so we do have a few pictures, but not much, because they land and then they melt, because the temperature on the surface is ungodly. It's like 700. I forget if it's Kelvin or Celsius or Fahrenheit, but it doesn't really matter. The metal melts, and so these probes don't last long. Here's a picture of one of our landers on Mars. This is the Viking, one of the 2 Viking missions from the 70s. And this was exciting. I grew up, I was born in 74, which is right at the beginning of kind of our exploration of the solar system. There were a few missions before I was born, but not many. So I got to witness this for the first time. You look in your textbooks and you see all these pretty pictures or on the internet and you're like, ho hum, yeah, we know what that looks like. But when I was a kid, we had no idea. And this was the first time we were landing on things and flying by things. It was really exciting. So this is the Viking mission, one of the 2 from the 70s. It was just a lander. It didn't go anywhere, but it came with all sorts of instruments and studied the soil. And then we forgot about Mars for a while and started going back in the late 90s and 2000s. We had a mission in 97 called Pathfinder, which is kind of just practicing getting back into it. And it did have a little rover. It was about this big. It's really small. You can see its solar panel here, called Sojourner. And then in 2004, we sent 2 of these. This is a mock-up because when this picture was taken, it was already on Mars. This one actually went to Mars. It's either Spirit or Opportunity. And I'll show you how they landed. That's probably how we'll end today because it's fascinating. They were only designed to go for about 3 months. And then the solar panels would get so caked with dust that they would shut down. And we sent 2 of them because at that point in time, half of our missions to Mars failed. Either they, sometimes it's because we entered yards instead of meters into the computer and crash landed. That actually happened. But it's hard to do. And so we sent 2 of them. And Spirit lasted 6 years and Opportunity lasted 14 years. And the reason why is there are these little mini tornadoes. They're called dust devils. You've seen like on a frozen lake, you may see the wind twirling. They come by and they clean off the solar panels. And so the missions went for years and years and years and very successful. Let me show you how we landed these things. A little terribly low resolution animation here, but here we go. So it takes 7 months to get there. Here it is coming in. So we have a heat shield, and Mars does have an atmosphere, but it's really thin. It's about 1/150th the density of ours. So it's not as, you're not going to get as hot going through. That's not the problem, but it doesn't slow you down either because it's barely there. You're still going at almost the same speed you came in. So we have the parachute, but again, there's barely any air, carbon dioxide air to grab onto. It doesn't slow you down much. Okay, we're deploying. We have Spirit or Opportunity in there. And it's coming down way too fast. It would crash land. But here's our plan right there. This is how they decided to do it. We're going to bounce land it. And boy, you have to test the hardware. We call it shake and bake. When you make spacecraft missions, even if they're not going to land, they have to go through rigorous heat and vibration testing. But this really had to go through the vibration testing. I was skeptical, and I watched when this first one went down. There's no radio contact during this stage when it's rolling around, right? Because it can't deploy its antenna. You're totally blind. You've lost contact and you wait for about 15 minutes for it to stop rolling. And they tend to settle in little craters. And you just wait for it to deploy itself and reestablish contact. So it will deflate the balloons. I guess that's not in this animation, but it deflates the balloons and it opens up and deploys itself. And it's designed, it doesn't matter how it lands, it's a tetrahedron. It can flip itself over and off it goes. And just to finish up Mars in the last minute or two, now we're on the surface, roving around for decades, right? Or a better part of a decade, a little bit more than a decade for the other one. So we have just tremendous wealth of data from the surface now, these close-up pictures and samples and everything. This is the last thing we put on Mars. This is Curiosity. So they're getting bigger and bigger. You can't bounce land this. This is the size of a small vehicle. So they came up with the most ingenious thing, and I actually bet money against it. And I'm an eternal optimist, but from an engineering point of view, so many things had to work for this to actually land. It is a jet-powered sky crane. The thing made it all the way through, and then this thing fires its jets, holds itself there while it lowers the rover, and then it detaches and flies away. The odds of it actually working were so small, yet it did work. And there's there's a video called 7 Minutes of Terror. And I want you to watch it. I linked it in the WebAssign announcement area. And this is one of the most marvelous engineering accomplishments, aside from landing humans on the moon back in 1969 with the technology of that day. So watch that video. And then next time we'll pick up with the missions to the outer solar system. Okay, thanks a lot.
Thank you, Doctor.
My pleasure.
Thank you.
Thank you.
Thank you.
Hey, Dr. Reichert.
Thank you.
Thank you.
Dr. Riker, I had a quick question.
Yeah.
I was wondering, so for the lab course, are they having like an actual lab today or not? I wasn't completely sure about that.
Let's see, this is, no. So lab 4, we scheduled over 2 weeks, because if you were on campus, there was a manual activity that would have to be socially distanced. So I think all the TAs met last week with you, right?
Yes, we did.
Yeah, so there won't be a meeting this week.
Okay.
I don't think.
Yeah. Did we have to do anything in Skynet for that one? I was a little confused about that one.
Yeah, so lab 4 it starts with a manual component just to reinforce the idea of how we make these measurements. But most of the lab is then astronomical Skynet stuff. But I'm sorry, there's an afterglow component, but there's no observation that you need to make.
Okay.
We'll be using archival data. Normally the TA would collect one data set for everybody, but since it requires simultaneous observations from telescopes in both hemispheres, and my southern hemisphere telescopes are closed because of COVID. So archival data.
Okay. Thank you, Dr. Riker.
Sure.